and we make products for training, and we are somewhat different than typical training providers. We don't provide training, we give you infrastructure to set up a training program at your place. So you buy these simulators, we make whole variety, all you see here, and we have more even than this. One of them, and then you can do the experiments, what I'm going to talk today also. And we did last 3 days essentially. And you can do all those experiments, and we sell to all companies, everybody. And they buy it for internal training, they buy it to bring the new guys on board. And so right now what I'm going to do is I'm going to go over the critical speed and resonance issues that happens in almost every industry, okay? And from aerospace to whatever. Because that's the inherent property of any system, okay? And that's law of nature, so you got to follow that thing. So ask me any question, you have anything? There we'll write down and explain you. So what I'm going to do today is this is a 2-session, and first half I will cover the basic background of resonance. I mean, I build up the whole thing, how the resonance occurs, and mathematical, without going into math, okay? Mathematical structure, and then show you the physical aspect of it, and what you do about it, and those kind of things we'll discuss later on. Just so you will have good physical understanding of resonance is there everywhere. It's just unavoidable, okay? It's just some certain condition has to be satisfied. Once that happens, it's all F is equal to ma, what we learned in high school, physics and all those things, okay? That's what resonance is all about, okay? And I'll show you what that means. And after that, we have set up this machine here, and this is right now with the fluid bearing, okay? And we'll go through critical speeds, okay? And we'll run some, we need to do some hammer test also. So we'll see the difference between static and dynamic case, okay? So just put 3-4 accelerometer on top of disc or on the side of the thing, and then we tap on the anywhere, okay? And then you'll see the more shape of those things, okay?
You want to do a break, and during the break, what can you start?
Yeah, during the break you can set up that thing, okay?
Yeah.
We'll take a 10-minute break in between so that we can do static as well as dynamic, okay, measurement, so that you understand how we do the static cases also, okay? That'll be the way to do, okay? And Nick, let's put one loader on that one. We have a loader for that, right?
A loader?
Yeah, maybe the...
No, there's one on the table.
What's your 5/8?
That's right.
5/8, it doesn't matter, it'll be, yeah, 5/8 you can put here. And then we'll do one here also, so I can describe the difference by what we are seeing, okay? Okay, let's get started. So, my title says basic theory, how to measure and develop control strategy. Those are the 3 items I'm going to focus, okay? Let's start with a little demo that we all have seen, but it's good to review that again and again, okay? That's Cody's Tacoma Breeze thing, and that's available public domain, so now they made it available to anybody, and I use it whenever I give this talk to show what resonance can do. This is nothing but a resonance, oscillation in the resonance. Very little energy is needed to move certain big thing. You can move a big building, train, if you excite at a certain right frequency. That's the key thing. And this case is the flow-induced vibration. The excitation came from the wind, and all it was is just the frequencies match. And essentially, in terms of forces, you have elastic forces that are associated with the steel and springs and all those things, and then inertia forces that are associated with the motion. Okay? So, in terms of energy, you're talking potential energy and kinetic energy, and those two forces match, and system is in equilibrium, and all you need is anything that excites it can move it. So that's all resonance is all about, and let's build that thing, how that happens, okay? And so just a few definitions that will be helpful to when we go into detail of this topic. One of them is what is vibration? In vibration, we say repeated motion, oscillations, and all those things there. But physically, what is happening is that you have a kinetic energy that is associated with the motion, 1/2 mv square, okay? And potential energy that is associated with the stretching to bending, position, or whatever you call it, okay? So several ways. So you have as an engineer, I may call it strain energy, okay? Elastic energy, whatever, okay? And that's all these are potential. That's coming because of the position, not because of the due to the motion, okay? And so those two energies are, when the thing is vibrating, they are trading. When it comes in the center, you have maximum kinetic energy. When it goes there, velocity goes to 0. So now you got kinetic potential energy because the energy is stored as a spring. That comes back. So these energies are going back and forth, trading. That's all the vibration is always happening. They are going on. As long as there is no loss of energy or anywhere energy is gone, then this trading can go on for infinite time. No reason. So if you take a beam and put in a vacuum, you'll see it will vibrate for much longer time than in the air, because air also has some kind of friction, okay, and that takes the energy away from the system. So vibration in the simple language is a exchange of energy between the two types of energy that we typically mechanical engineer associate as kinetic energy and potential energy. Okay, and according to the excitation, we have two types of vibration. One is the free vibration that occurs without any source. You just excite it somehow, bang on it something or pull something, and then it keeps going, okay? In that free vibration, the trading is going on all the time, okay? And in that case, you operating in equilibrium. Means your forces are balanced there. Means that's going to happen at natural frequencies only. Very important concept. The free vibration are only at natural frequencies of the system. It's not happening at your forces that you use, or rotating forces or anything. So, and normally a lot of time when you see some extra frequency comes up, that's sometimes is the natural frequency which has nothing to do with your it has to do with the structure, but it's not the belt frequency, or it's not the gear frequency, or it's not the coming from the bearing and all those things, but those frequency excited the nature. And then there is something called force frequency that comes because you're forcing something. You are unbalanced. That's your mr omega square, right? Omega square term is a forcing something. That's a force frequency. So in a machine, we have often when we take the vibration data, we are talking about the force vibration. But this resonance still keeps coming. That's coming because at certain point you pump the energy that excited those resonances, okay? Okay, here's another thing. This is a free vibration and the beam will keep on going back and forth. If you, please give me a card, I'll be glad to send you an electronic copy of the presentation, okay? Just give me a card, I'll be glad to send you, okay? This is not a proprietary, we educate people, so we don't mind giving that, okay?
So we don't need to take notes then, you're saying?
Yeah, I know you can write it. Sometimes it's always good to refer notes. When I was listening to, I write to something, so that's for my own purpose, okay? But you don't have to worry about the detail. I'll send you a copy of this thing, okay? Okay, there's another way. Here is a little bit illustration, okay? Here this is excitation. Now on the left side, I have excitation, slower motion excitation. Oh, already. Good. Okay. So we have a three position of the beam, spring and mass here, okay? And I'm exciting at three different speeds or three different frequencies. On the left, I'm exciting at the slow. On the middle, I'm exciting at the resonance. we want to call, and then here I'm exciting it fast on the right side. Okay. So now let's see that what is happening here. When we exciting here slow, see your excitation force, they are moving in the same direction. Here they are sometimes same, sometimes opposite, 90 degrees. Here they are opposite to each other. Your excitation is up, then motion is down. Excitation is down, motion is up. So this is above resonance, this is at resonance, this is below resonance. Now, once we understand this thing, let's say first place we're going to take advantage of this thing is balancing. We balance a machine based on, I'm not talking sharp balancing, I'm talking the field balancing, okay? Based on the vibration. We take the vibration data and say, okay, there is unbalance, now how do we correct it? We have software or whatever, we have data collector, we do it, to take the phase measurement and then say, okay, the vibration is maximum on this at 45 degree to a reference point, and now what I do? Okay, I go to minus 45 degree and put a correction weight and do the couple of trial, and then we figure out. So you're going to put the correction weight opposite to the force vibration. But if you're doing above critical, you're going to put in the same direction. My vibration is maximum here, I'm going to put correction weight here too. Because what we're trying to do is we're balancing a force, not vibration. Keep in mind, we balance force. We want to cancel the force out. This is the force vibration, so you want to cancel the force out that's acting on the machine. And vibration is the cause of the force, not, it's not the, it's a symptom, okay? It's not that you're trying to correct. And the goal is to minimize the vibration. But what you're really trying to do is you minimize the forces acting on the system. And so that's the reason you put opposite with below critical. Above critical you put the same direction, and at critical it's very difficult to balance because your phase is shifting. You take the data here, the next time it will be different. So your phase is always moving around at the critical, so that's very difficult to make, do, and only technique that works well is the 4-run method where you don't need phase anchor. You just rotate 90 degrees and keep changing the weight. 120 degrees at 3 locations, okay? First. Okay, so this is now we're setting up the foundation here, okay? Now in a machine, you can think machine as a dynamic system, a little bit an engineering term here, okay? We call dynamic system, and a machine also, or whatever dynamic system we have when we describe mathematically, we say there are 3 elements to any system. One is a spring, another one is a mass, another one is the energy dissipation, energy taking away mechanism, and we call that a dashpot, okay, right? And so we have a mass, spring, and dashpot. These 3 things together describes a system. And in the mass, you store energy due to motion or kinetic energy. In the spring, you store energy due to the position or deformation, okay? And that's the potential or strain energy or elastic energy, okay? There are various terms associated with this thing. And the damper is a mechanism that takes the energy away. As I said, air has a damping because there is a friction, right? So that's anything that takes the energy away is a damper. Okay. So this is a spring mass, just a representation of it. You can represent this machine parts also this way, okay? And you have mass, this is the potential energy, this is the this is the kinetic energy, that's the spring is the potential energy, and the dissipator is the energy taking away. There is nothing like a really viscous damper, okay? But that's the idealization we do, and we can learn a lot from that alone, okay? Finding a pure viscous damper is almost impossible because even if you take a piston, there is a spring with it, okay? It's not pure viscous, okay, when you start moving. But we need something like this to make sense out of the data, and calculations are pretty close, so it's not that they are off, okay? So now in our case of machine, we're going to have 2 directions. There is a horizontal stiffness and vertical stiffness, and it's important that machine is going to be like this, not the previous case, because a lot of time in the measurement you see 2 peaks. Nothing is perfectly things 90 degrees, nothing is perfect here, accelerometer, maximum vibration direction, okay? So when you're putting accelerometer horizontal and vertical, the maximum vibration could be at 60 degree to horizontal or 30 degree to horizontal, okay, right? And so you're going to see the component in the horizontal and vertical direction, and sometimes you may see two frequencies nearby, and those are resonances in horizontal and vertical direction sometimes. Not all the time, sometimes. So that's the reason we always have to think in terms of there are going to be there can be two peaks, and that's because you have a horizontal stiffness which is different for a machine than the vertical stiffness. Usually mass may be the same, but the stiffnesses are going to be different. Trying to move this machine this way is different. It's easier sometimes because of this makeup of the machine. You're moving vertically up and down, right? And that's why you can get especially on the first critical, that makes a difference, you will see. And you will see sometime when you're doing that thing in the fluid bearing, the region between those two critical speeds is dangerous. That's where you can get unstable flow also, and that can be reverse whirl can happen, and that can destroy your machine. This is not a course in rotordynamics, so but there are two frequencies that you may see time to time in your data. Okay, if you are a perfect motion horizontally moving, then you only see one, but usually your accelerometer may not coincide with the exact frequency. That's why you can see two frequencies. Okay. That's the reason I brought up that picture to show that machine you may get that kind of thing. Okay. So now this is the way. Now what we're going to do is we're going to build up the resonance idea from right here, from this simple-minded thing. Okay. And now the way we describe machine spring is that spring is something that stores energy due to deformation. Means it's not function of speed. It's that how much totally you deform it. It has nothing to do with how fast we deform it and how slow we deform it. It's how much you deform it. Okay? And that is a spring, classic definition, right? And so it's the definition here. This is the force. We apply a force. It moves a certain amount, and the resistance is called stiffness. Okay. And if you look in terms of frequency, then it's going to be same. K is the same. K is not changing. You apply whatever frequency you want. 10 Hertz, 20 Hertz, 50 RPM, 100 RPM, doesn't matter. How much you move, that is important. So that is a mathematical representation. So if you take the compliance, or that tells you softness of the or stiffness of the how hard it is to move certain thing, then we define per unit motion per unit mass, okay, per unit force, sorry. And so you take motion over force, and we call compliance, okay. That's the typical definition, and that's given by this equation. So if you take this thing and you take the ratio at any frequency, it's going to be constant for spring. Okay, and then graphically we'll show this thing like this. If I plot is a function of frequency, it's always constant, one parallel line. It doesn't change. That's a classic definition, okay? And you'll see that resonance will pop up from here in a couple of more slides. Okay? So here, repeat, spring stores energy due to deformation. So in a machine, you can, any part can be a spring, okay? And property do not change with frequency. No matter how fast you're running the machine, no matter how slow you're running the machine, it's the function of how much you deformed it, how much you moved it, okay? Now the mass, whereas the mass is related with the acceleration, okay? If you're accelerating something fast, you need more force, right? And so that force-mass relationship, so we are defining the relationship between force. We said vibration is a trading with the kinetic energy, right? And potential energy. But that does not allow us to develop a theory. Law of nature say force are balanced, right? Newton's law doesn't say about the kinetic energy or anything. All Newton's law tells us is the F is equal to ma. If we don't move something, don't apply the force, things will not move, right? So it's the force. So we have to bring back that thing into force right now. That's why we are developing ideas, relation between force and the motion. Okay, so the mass, force and relation is the mass times acceleration is equal to force. And that's the inertial force. That is the part relates to the kinetic energy. Okay? And this is the acceleration, this is the mass, and that's the force required to accelerate certain thing. But now if you write this thing x is equal to sinusoidal function, then you're going to get, you differentiate twice, you're going to get omega square x omega, right? And they are equal. So now if you take a compliance of mass, then that will be a function of omega square. Higher the omega, lower the compliance. I mean, yeah. See, it keeps going down. Okay. So now if I plot this equation as a function of frequency, then I will get a curve like this. The mass increases, then this curve shifts, and if I have to move something right here, I need lower force. But if I have to move here, I need a lot more force. Alright? So you have mass line that decreases a compliance line, okay, associated with the mass. If I have to plot like a stiffness, dynamic stiffness, then this line will go like this, okay? The system become more stiffer at high frequency.
That line is straight because you use a log scale.
Log scale. I drawn on the log scale, so that's why you see that 0.1 hertz, 10 hertz, and this I'm showing you on the 10. Okay, so this will be log scale. Okay. I mean, just shown here is otherwise on the real spec this will be minus 1, 0, 2, 3 like that, right? Purely log scale, but the numbers are written in the linear scale case, okay? But the scale is log. Same thing on the y-axis, okay? It's a log plot, because if you take, let's go back. Okay? If I take log plot, then I take the log of this thing and then we can divide it and we're going to get a straight line, okay? And that will, the slope will be 20 dBs per decade. Let's not worry about that part, okay? When we do the modeling, we get carried away. Okay? So we do, and this is the line. Now, you got these two lines, right? One is going straight, another one is coming down, right? Now, at some frequency, your elastic force or the potential, the terms that associate potential energy and the inertia force, they're going to be equal. They have to be for a given motion, okay? At some frequency, they're going to be equal. And when they are in equilibrium, our system is in equilibrium. That frequency is natural frequency. So let's draw and let's just introduce the idea of this dissipator also, okay? So in here, we assume our dissipation or the energy loss mechanism is proportional to the velocity. Again, Newtonian concept, okay? Kinematic viscosity, that's the original thing, more work was done by Newton in there also. Right? And then a lot more work was done afterwards. So here, if you take this one and then you plot this one, compliance here, then you see it decreases with this omega linearly though. In the other case, it was decreasing square. Okay? And if you plot this line, the compliance line, it goes slower with omega. The mass line goes faster because it's square. Okay? Now, to develop the concept of the inertia, take this case here. I have given a picture here. In this, we have spring force and inertia force. At some point, these two forces become equal. And we go back. So this is same thing we wrote in a frequency domain as a function of rate, okay? No new thing here, just mathematical calculation. Now, if we draw, I can plot those two curves and these two, the point where these two lines intersect, okay, is resonance frequency or natural frequency of system. So a system can have several natural frequency and we can plot intersection point associated with each natural frequency. So there is a part of the mass is moving this frequency, part is moving this frequency, and you have lots of resonances, but the key thing is that your forces are balanced at this point. And now if I take any external stimulus, then I can move whatever I want, tiny force. Okay, it's balanced. Those two, the quantities are balanced. So resonance is the large amplitude excitation at the natural frequency, because I can move the system with much larger amplitude at that frequency, only at that frequency. That's it, one frequency where these two forces are balanced. Your inertia forces are balanced with elastic forces, the energy that stores in the spring. The inertia forces that opposes the motion, okay, right? And the spring stores and it wants to restore back to the neutral position. So your mass is going up. And so now, once you go over the resonance, then inertia wants to stay up and elastic forces are want to bring it back. So let me draw a plot here so I'll explain better this way, okay? And our damper, what damper does it keeps the motion under control. It will not allow it to fly away, okay? It just keeps under control. Okay, so we get a curve like this. We have no damping, then at this point, if I come to this frequency, then I can move it, whatever I want, without damping. But there is always some friction. There is always some inherent in the material even, okay? Because no material electronically also is totally elastic. There is always the atomic scale also there is a friction there, okay? So even sometime due to the void in the material, sometime due to mismatch in the atomic structure, whatever. So there is always damping is inherent in everything. So there is always some energy gets lost, okay, as a heat. Normally when we talk about, when I'm talking, this acoustic energies, all of them, everything gets dissipated. There is no dissipation that my voice should go travel all the way, right? It does not, because dissipation is happening or it's bouncing in some case to the wall. That's a different phenomenon. So dissipation or energy loss is inherent in everything. You can minimize it, but you cannot totally eliminate it. And so this is what keeps this thing. But this understanding of this curve is very important. I find it very useful to me. If I had to, let's say I found out through some test that we're going to do today, okay? This point, okay, on this situation. Then I want to, my machine is running in this area. So I'm going to get large motion. So if my motion is high, the bearings are going to fall apart, may get cracked, may get fatigue failure, or any kind of failure. So what I'll do, my goal is, this is my operational speed, right? You can't change the operational speed because of the production needs, okay? Or whatever it may be. Easier is to change the operational speed, then you got no problem. But I can't change. So I say, what I'm going to do? Either I move my motion this way, or I move this way. Or I add damping. There are three solutions, that's it. Decrease the stiffness, then your natural frequency will go this side. Add mass, the natural frequency will go this side, okay? Increase stiffness, remove mass, natural frequency will go this side. And so this curve will keep coming like this and shift here. Or add damping, so this will keep control of the thing. Adding a damping on rotating machine is not easy, very difficult. There is one more thing we do, is the transformation of energy from one to another structure that we call tuned mass damper. Okay? And in the tuned mass damper is like a vibration also 2 degree of freedom system, 2 spring mass there. Okay? So here you design such a way that your main structure frequency coincides with the tuned mass damper. Okay? And so instead of your main energy in the main body, your tuned mass damper will move, okay, which you don't care. And to do that one, easiest way is like this. Let's say it's not going to be easy to apply on the rotor, but if you got a structure problem, then you can apply this thing, okay? So let's say we have a here, okay? So this is moving, right? So what you do is, this is a practical, what you want to do is you want to put another mass here, okay? And transfer the energy of this motion into this thing, okay? Now, that's easy said. How do you apply this thing, something like this? So what you can do, I have done it. I take this beam or something. Usually threaded rod is good. Then you can move. You don't have to worry about designing calculation. So you put a mass here. Both are one direction, doesn't matter. Okay. A lot of times it's good to put both sides. Okay. And then you keep moving till you find out that this flows. So instead of this thing moving, you're going to see vibration of this thing going. You can go either way, both way, or whichever is the constraint. That's not a problem. Okay. So all you did is you created a second degree of freedom here. So motion of this thing, which is going like this, with the forcing function here. Now this moves here. So if this breaks, you throw it away. This is a $10 solution. But if you got a rotor, that may not be easy. It may not, especially with the fluid film, okay? Because the energy is not metal to metal contact. The rolling element still you can. But this works only at one frequency. So I'm telling you about the solution strategy as we go, okay? And this is another formal plot, okay? Now this, another good thing, okay? Another very, very informative plot. So your machine has lots of this thing, okay? Just wherever you combine the stiffness, the elastic energy and the mass energy, and they balance out, you get resonance. You go to another frequency, then a small part, other part of the mass balances the other part of the springs, and then you get another natural frequency, okay? And so you can have several natural frequencies within a whole system, okay? But each one of them has a curve like this. That's very true. Each one of them is going to have this point where the forces, two type of forces are balanced. Now, in this region, you have stiffness controls your motion. In this region, mass controls your motion. In this region, damping controls your motion. If you apply damping, there is nothing you can do on this side. You're not going to do much on this side. Only in this 20 to 30% of the plus minus region, damping will be effective.
Are you going to discuss critical damping?
Yeah. Critical damping is that, when we take the equation,
I don't want to get you off.
I have something. I'll pull up. Give me 2 minutes. We can fire up June number software, right?
Yeah.
Huh? We'll show that thing, okay? We have a software that will allow you to show the critical damping, okay? We'll show you that, okay? Okay, so repeat. In this region, you're controlling the motions by manipulation of the mass, okay? In this region, you're controlling the motion by manipulation of stiffness, okay? And in this region, you're controlling the motion by manipulation of damping. That's it, very simple-minded thing. Once you plotted this curve for a given pair, okay, it's always